Now starting with this chapter with halogen compounds. The classification of halogen compound on the basis of the number of the halogen atoms. First one is monohaloalkane, second one is dihaloalkane, trihaloalkane, monohalobenzene, dihaloarene, trihaloarene. Nomenclature. The first one is N-propyl bromide, 1-bromopropane. Second one is isopropyl chloride or 2-chloropropane. Third one is isobutyl chloride, 1-chloro-2-methyl propane. Third one is bromobenzene. Fourth one is 1,2,1,3-dibromobenzene or meta-dibromobenzene or sim-tribromobenzene or 1,3,5-tribromobenzene. Next one is 1-chloro-2,2-dimethyl propane, and the last one is 2-bromopropane. These are the column of the structure and common name and UPAC name. Nature of the CX bond. Halogen atoms are more electronegative than the carbon. Therefore, the carbon-halogen bond of the alkyl halide is polarized. The carbon atom bears a partial positive charge, where the halogen atom bears a partial negative charge. As we go down the group in the periodic table, the size of the halogen atom increases. The fluorine atom is smallest and the iodine atom is largest. Consequently, the carbon and halogen bond length also increases from the CF to the CI. Some typical bond lengths, the bond enthalpies and the dipole moment are given in the table. CF bond length is shortest, CL bond length is greater than CF bond, then greater than CBr. CBr bond is greater than CCl bond, and CI bond is most longer, and the dipole moment of CF bond is 1.847, CCl bond is 1.860, CBr is 1.830, and CH3I is 1.636. It is observed that CH3Cl has highest boiling point than CH3F. It is due to the fact that the dipole moment mu depends on the charge and the distance of the charge separation. So CF bond is shorter and CCl bond is slightly greater than the CF bond. So dipole moment is slightly higher than that CH3CF, 1.860, where CH3F is 1.847. Preparation of the halogen compound. The aliphatic halogen compounds can be prepared from alcohol with giving the reagents such as HCl, ZnCl2, NaBr, H2SO4, PX3, PCl5, red phosphorus X2, where is Br2I2, ROHSOCl2 is RCl. So like that we can prepare the halogen compounds from the alcohol. We can prepare the halogen compound from alkane with the controlled allotment of halogen compound in presence of UV light or heat. So it can produce in this reaction the butane is converted into N-butyl chloride or some isobutyl chloride. So from alkene, in addition reaction of the HX, from terminal alkene with the addition product, it will follow the Markovnikov addition rule. From dibromo, with the reaction with the dibromo compound with alkene in presence of CCl4 as a solvent, so dibromo compound will be formed. The preparation of haloarenes. First one is toluene reacted with halogen in presence of Fe dark. So it will produce ortho and para product. The para product will be the major. And the second reaction is from amine. First one is the preparation of the benzene diazonium salt, and then the Sandmeyer reaction with the benzene diazonium salt to produce the haloarenes. Now there are some problems. Draw the structure of the major monohalo product for the following. The first one is cyclic alcohol with SOCl2 will give the chloro product. Then here Br2 heat or UV light, it will produce the monohaloalkane. Monohalo compound. Third one will also produce monohalo compound. Fourth one, there will be also addition product. Fifth one, there will be substitution product. And the sixth one, there will be actually addition product of the bromine. Melting and boiling point. Methyl chloride, methyl bromide, ethyl chloride, some chlorofluoromethanes are gases at room temperature. Higher members are liquids or solids. As we have already learned, molecules of organic halogen compounds are generally polar. Due to the greater polarity as well as the higher molecular mass as compared to the parent hydrocarbon, the internuclear force of attraction or dipole-dipole interaction and van der Waals forces are stronger in halogen derivatives. So that is why the boiling point of the chlorides and the bromides and the iodides are considerably higher than those that of hydrocarbons of the comparable molecular mass. The attractions get stronger as the molecular get bigger in size. The molecules get the bigger in size and have more electrons. The pattern of the variation in the boiling point of the different halides is depicted in the figure this. For the same alkyl group, the boiling point of the alkyl halide decreases in the order Ri greater than Rbr greater than Rcl greater than Rf. The boiling point of Ri is greater than that of Rf due to its molecular weight. Now this is because with increase in size and the mass of the halogen atom, the magnitude of the van der Waals force increases. The boiling point of isomeric haloalkane decreases with the increase in the branching. For example, 2-bromo-2-methyl-propane has the lowest boiling point among the three isomers. The boiling point of the isomeric dihalobenzene are very nearly the same. However, the para-isomer are high melting point. Para-isomers are high melting point as compared to the ortho and meta-isomer. It is due to symmetry of the para-isomer that fits in the crystals lattice better as compared to the ortho and meta-isomer. The para-isomer has the highest boiling point due to the symmetry. Boiling point of the 1,4-dichloro benzene is 448 and to that of meta-dichlorobenzene is 446 and orthodichlorobenzene is 453. So orthodichlorobenzene has highest boiling point than the para, because it has also symmetry, and as well as it has a neat non-zero dipole moment, but the para dichlorobenzene has dipole moment almost zero. But there is a huge difference in the melting point. The melting point is in orthodichlorobenzene is lowest, but the paradichlorobenzene is the highest. It is because of the symmetry. Symmetry presents here. Density: bromo and iodo and polychloro derivatives of the hydrocarbon are heavier than the water. Thus, the density increases with the increasing the number of the carbon atoms in the halogen atoms and the atomic mass of the halogen atoms. Solubility: haloalkanes are very slightly soluble in water. In order to dissolve the haloalkane in water, the energy is required to overcome the attraction between the haloalkanes and the molecules and break the hydrogen bond between the water molecules. Less energy is released when the new attractions are set up between the haloalkanes and the water molecules, and these are not the strong as the original hydrogen bonds in the water. As a result, the solubility of the haloalkanes in the water is low. However, in haloalkanes they tend to dissolve in the organic solvent because the new intermolecular attraction between the haloalkanes and the solvent molecule and have much same strength as that one being broken in the separated solvent. Reaction of the haloalkane: nucleophilic substitution reaction, elimination reaction, reaction with the metal. Nucleophilic substitution reaction, SN2 process, it is backside attack. So the order of the reactivity is for SN2 is primary halide greater than secondary halide greater than tertiary halide. Primary halide greater than secondary halide greater than tertiary halide. Configuration: the special arrangement of the functional group around the carbon is called configuration. The special arrangement of the functional groups around the carbon is called its configuration. What is configuration? The spatial arrangement or the spatial arrangement of the functional group around the carbon is called configuration. Let's see the structure A and B, which has mirror image relationship. These two structures of this compound are called enantiomer. SN2 process for trimethyl butyl bromide. Step 1 is the dissociation of the bond and the formation of the carbocation, and the step 2 is the formation of the alcohol 2 methyl propantuol, 2-methyl propantuol. For SN2 reaction, tertiary halide, the reaction follows in the order primary halide more than secondary halide more than tertiary halide, and for SN1 reaction it is reverse. Tertiary halide will participate in more in SN1 reaction. SN1 reaction are very fast because the higher stability of the 3-degree carbocation, we can sum up the order of the reactivity of the alcohol in the as follows. For the same reason, the allylic and benzylic halides show the higher reactivity towards the SN1 reaction. The carbocation thus formed gets stabilized through the resonance. The reactivity order is Ri greater than Rbr greater than Rcl greater than Rf. Chirality. An object that cannot be superimposed on the mirror image is called chiral. So these are the picture of the chiral. So propantuol is prochiral, almost chiral. The location of the alpha and beta carbon. For halogen compound, this carbon is alpha carbon. For this carbon is alpha carbon and the adjacent carbon is beta carbon, and the attached hydrogen is beta hydrogen, and the reaction will called the beta hydrogen elimination reaction. The first one is E2 reaction. As a result, alkene is formed as a product. Since beta hydrogen atom is involved in this elimination, it is often called as beta elimination process. As a result, an alkene is formed as a product. For an unsymmetrical alkene like 2-bromopentene, if it is given alcoholic OH, then pent-1-ene and pent-2-ene will be product. Will be two types of product. The major product will be pent-2-ene, which is 81%. Elimination versus substitution product. Reaction with metal. Grignard reagent. The alkyl halide reacts with magnesium in presence of dry ether to form a Grignard reagent, which is the first organometallic compound, sigma bonded organometallic compound ever known. The important class of organometallic compound discovered by the Victor Grignard in 1900 in alkyl magnesium halide. The Grignard reagent is a reagent. The carbon magnesium bond is covalent but highly polar, with the carbon pulling electrons from the electropositive magnesium. The magnesium hydrogen bond is essentially ionic. RMgX. The Grignard reagents are highly reactive and reacts with the source of the proton to give the hydrocarbons. Even water, alcohol and amine are sufficiently acidic to convert it RMGX to RH and magnesium hydroxide. Next reaction of the halogen compound alkyl halide when reacted with sodium in presence of hydrocarbons in presence of hydrocarbon or dry ether, it will be converted into alkane. Resonance effect. Chlorine is orthopara directing group. The replacement of the chlorine in presence of NaOH along with 623 Kelvin and 300 atm temperature with the first condition, and second condition is H plus, it will give the phenol as a product. In the presence of electron withdrawing group NO2 at the ortho and para position will increase the reactivity. Para-nitrochlorobenzene will give the para-nitrophenol as a product. 2,4-dinitrochlorobenzene will give 2,4-dinitrophenol as a compound, and third one is 2,4,6-trinitrochlorobenzene will give a picric acid as one of the product, 2,4,6-trinitrophenol as one of the product. It is called picric acid. So first one, the reaction condition is very harsh to replace the CCl bond from the as it is sp2 hybridized. The carbon atom is sp2 hybridized, and it is and the Cl bond is not a single bond. It is like more than a single bond or close to a double bond due to the resonance effect here. So to break the CCl bond in the aryl halide is difficult, so the hash condition is put here in the first reaction. In the second reaction, the nitro group generates a positive electropositivity on the electrophilic carbon atom, and the hash condition relaxed, and the condition relaxed with 443 Kelvin temperature with no pressure. In the third reaction, the reaction condition is more relaxed also to give the product, and in the last fourth condition, warm water, no basic medium is needed, only warm water is needed to produce 2,4,6-trinitrophenol or picric acid as one of the compound. The effect is pronounced when nitro group is introducing an orthopara position. However, no effect on the reactivity of the halogen is observed by the presence of the electron withdrawing group at meta position. The mechanism of the reaction is depicted here. Here OH group is directly attacking at first the p orbital and then replace the Cl minus ion. And then the formation of the sigma complex. Then the sigma complex is converted into the phenolic compound. The first step is very slow steps, and the last step is fast step. Halogenation reaction. In presence of chlorine and anhydrous FeCl3, 1,4-dichlorobenzene is found as a major product, and 1,2-dichlorobenzene is found as a minor product. And nitration occurs in the product, and HNO3, the concentrated H2SO4. The formation of the nitronium ion will produce the para product as a major product, 1,chloro,4-nitrobenzene, and sulfonation with the reagent with concentrated sulfuric acid and heat will give the sulfonated product. With orthopara substitution, the para product will be the major product. Friedel cap alkylation reaction. The chlorobenzene can also undergo the Friedel cap alkylation reaction with CH3Cl with anhydrous AlCl3 will give the orthopara reaction. Para will be the major product. And Friedel cap acylation reaction, acyl chloride in presence of anhydrous AlCl3 will give the ortho and para product. Para will be the major product. Wurtz fatigue reaction, in presence of sodium and dry ether, the aryl halide and alkyl halide will combine with each other to give an aromatic alkane compound. Wurtz fatigue reaction, and fatigue reaction is the combination of the the two aryl halide in presence of same reaction condition with sodium dry ether to give diphenyl. Dichloromethane. Dichloromethane is widely used as a solvent, as paint remover, and the propellant in the aerosols. As a process of the solvent in the manufacture of the drugs, it is also used as a metal cleaning and finishing solvent. Methylene chloride harms the human central nervous system. Exposure to lower levels and the methylene chloride in air can lead to slightly impaired hearing and vision. The higher levels of methylene chloride in air causes dizziness, nausea, tingling, and the numbness in the fingers and toes. In humans, direct skin contact with the methylene chloride causes intense burning and mild redness in the skin. Direct contact with the eyes can burn the cornea. Trichloromethane or chloroform. Chemically, chloroform is employed as a solvent for the fats and alkaloids, iodine and substances. The major use of the chloroform today is the production of the freon in the refrigerator R22. Production of the freon in refrigerant R22. It was once used as a general anesthetic surgery, but has been replaced by less toxic, safer anesthetics such as ether. As might be expected from its use as anesthetic, inhaling chloroform vapors depresses the central nervous system. Breathing about 90 parts of the chloroform per million or 900 ppm for a short time can cause dizziness and fatigue or headache. Chronic chloroform exposure may cause the damage to the liver when chloroform is metabolized to phosgene and to the kidneys, and some people develop sores when the skin is immersed with the chloroform. The chloroform is slowly oxidized by the air in presence of the light to an extremely poisonous gas, the carbonic chloride, also known as the phosgene. It is therefore stored in the closed dark colored bottles of the comply with the filed with so air cannot be kept out. 2CaCl3 with oxygen in presence of light, COCCl2, which is toxic phosgene gas. That's why the chloroform is kept in closed dark bottles. triiodomethane. It was used earlier as antiseptic, but antiseptic properties are due to the liberation of the free iodine and not due to the iodoform itself. Due to its objectionable smell, it has been replaced by other formulation containing iodine. Iodoform can be used as antiseptics. Freons, chlorofluorocarbons. Chlorofluorocarbon compounds of methane and ethane are collectively known as freons. Chlorofluorocarbon compound of methane and ethane are collectively known as freons. They are extremely stable, unreactive, non-toxic, non-corrosive and easily liquefiable. Freon 12 CCl2F2 is one of the most common freon in the industrial use. It is manufactured from the tetrachloromethane by Schwartz reaction. These are actually produced by aerosol propellants and refrigeration and air conditioning purposes. By 1974, the total freon production in the world was 2 billion pounds annually. Most freon, even that used in the refrigeration, eventually makes it away into the atmosphere where it diffuses the unchanged into the stratosphere. In the stratosphere, the freon is able to initiate the radical chain reaction that can upset the neutral ozone balance. Next, another compound is DDT, dichlorodiphenyl trichloroethane. It is a chlorinating organic insecticide. It was originally prepared in 1873, but it was not until 1939. Paul Muller was awarded Nobel Prize in Medicine. Paul Muller was awarded the Nobel Prize in Medicine and Physiology in 1948 for his discovery. The use of DDT increased enormously and worldwide and basis after World War II, primarily because its effectiveness against the mosquito and the spread against the malaria and the lice. They carry the typhus. However, the problem related to the extreme use of the DDT began to appear in the late 1940s. Many species of the insects developed resistance to the DDT, which was discovered to have highly toxicity towards fish. The chemical stability of the DDT and its fat solubility related to the stored in the fatty acid tissue. If investigation continues at the steady rate, the DDT builds up with the animal over the time. The use of the DDT was banned in United States in 1973, although it was still in use in some other parts of the world. This is the structure of the DDT. Thank you. This is the end of the chapter of the haloalkanes and haloarenes.